Does anyone have administrative questions before we begin? Oh, thanks to Selena, outstanding suggestion. I'm going to be posting God willing, I'm going to do my darndest. It's been a week, let me tell you, but I'm going to do my darndest to get the practice, homework, practice, midterm, reopening quizzes, reopening old homeworks for this module. I'm going to do my darndest to get that open by the beginning of spring break. So you can have all break and all of review week. You'll have 2 weeks to go over that stuff. Hopefully that will be useful and helpful. Okay, so capacitors, capacitate. Let us capacitate. Review a little bit. You should already remember some of this at least. I presented a starting point for capacitors is that the electric field is not kq on r squared inside a capacitor. Inside a capacitor, the electric field is a very simple equation, charge density divided by a constant. Charge per square meter, q over a, divided by epsilon naught. That 8.85, 10 to the minus 11. 10 to the minus 12, for God's sake. By the way, pro tip, as some of my students have discovered, if you get the constants wrong, your problems end up being much harder. So I encourage you to make sure that you have written down the numbers correctly here. I'm going to write this down again. 8.85, 10 to the minus 12, not 18.85. Watch out. Having correct numbers usually helps problems. Okay, so. This should be in your notes from before, though. We've been seeing this again and again. Oh, also, if I forget to give you constants like this on exams, you're always welcome to ask. I mean, hell, you can always ask anything on exams. I reserve the right to say no. You can always ask. Okay, so we spent, was it a week ago? Yeah, a week ago, we spent a fair amount of time on the relationship, the idea that voltage and electric field are related. We talked about the work-energy relation. And the change in voltage as you go some distance through a field is E times the distance you move along a field line. There is a minus sign in here. But for capacitors, we don't care about the direction of the electric field, the sign of the charge. In capacitors, we just ignore that. So I'm talking about the absolute value of the voltage difference here. Inside a capacitor, we don't care which way it goes. So if I plug E in, the voltage difference across the capacitor is, well, E is Q over A epsilon naught. The distance between the capacitor plates is usually given the letter D. Multiply D times E, you get QD over A epsilon. And reflect on this, my grasshoppers. There are two pieces of this. By the way, I will ask you about this. I will ask you to think about this deeply. Voltage is electricity. Charge is electricity. Everything else is property of the capacitor, distance between the plates, area of the plates. There are things called variable capacitors where these can be changed, but they're relatively rare. In general, unless I specifically state you're changing something about the capacitor, you can assume that distance and area of the plates are constant. Okay, so, just like with resistors, voltage equals current times stuff about the resistor, properties of the resistor that don't normally change. Samey equals samey. Same concept here. I am defining the ratio charge to volt as the capacitance of the capacitor, which means, solva, the capacitance of a parallel plate capacitor is A epsilon over D, A epsilon naught over D. Note, I think that I forgot to write this on the board my first pass through. The base unit of capacitance is the farad, named for Michael Faraday, great experimenter from the 1800s. So 1 farad is the same thing as 1 coulomb per volt. Please be careful, do not confuse the unit F for force, just like you need to be careful not to confuse the unit coulomb for capacitance. If I write number space F, that's a unit. Look, previously, last year, you would write like 2 space M. What does that mean? Does that mean 2 mass? something equals 2 space m. No, it means position equals 2 meters or whatever, right? If you put a number space, if you're specifying an answer, number space letter, that letter is the unit of the answer. If I said x equals 5m or whatever, x is the variable. In this case, c is the variable. And its unit is the, well, in x equals 5 meters, the unit is the meter. Here, the unit is the farad. Please. Yes. Let me double check that. It is? Okay. Okay, yeah. Thank you. Please always check with me, or always remind me. Okay, so, what the hell is capacitance? What's it mean? What's it taste like? Capacitance is not quite the capacity of a capacitor. Capacitor, our simple model for a capacitor is there's actually, you could store infinite amount of charge in them. But capacitance is how easy is it to store some amount of charge. Capacitance reflects how easy it is, how much charge you can store on the capacitor for 1 unit of voltage to develop across them. Why is this useful? In early static electricity experiments, we didn't have batteries. They hadn't been invented yet. A measure of how good your storage device, called Leyden jars, a primitive capacitor, measure of how good your storage device is how much charge you can get on there per volt being developed. Why per volt? Because you get high enough voltage, you'll get arcing, you'll get discharge. You get a spark that would short things out, and then the capacitor is, you've lost your charge for your experiments. So a measure of how many coulombs you can get per volt is sort of a measure of how good your capacitor is at storing charge. That's the origin of charge per volt. The larger C is, the easier it is to get a lot of Q, a lot of charge for each amount of voltage that you've got. I want you to distinguish. No, I insist you be able to distinguish between the definition of capacitance, charge per volt, and the particular equation, capacitance of a parallel plate capacitor is A epsilon naught over D. A epsilon naught over D is sometimes true. It is true for the kinds of capacitors that we are dealing with. It is not a universal truth. It is not a universal law. There are capacitors that are not parallel plates. We're not talking about them, but they have a different equation. They also relate to the size and shape, and not the electricity on the capacitor, but how big it is and its dimensions. But this is only true for parallel plate capacitors. Capacitance equals charge per volt. That is to say that there is a linear, a proportional relationship between charge and voltage in a capacitor. This is an always true statement. This is a universal law. It's a definition. Compare, by the way, Ohm's law, V equals I times R. There is no resistor that does not obey V equals I times R. We talked about a prism cross-section resistor has a equation, resistance equals resistivity times length divided by area. How do I make a given resistor? Well, bam. But once I know the cross-section, excuse me, the length and the resistivity, that resistor's resistance doesn't change because of the electricity. Is this always true? No. This is a particular equation that is true for a given resistor. This affects how much resistance a resistor has. This affects how much capacitance a capacitor has. But the idea of capacitance, the foundation, the always true statement that once you have a capacitance you can solve for the ratio of is this, charge per volt. Charge per volt is the meaning, coulombs per volt is the meaning of capacitance, and that is always a true statement. I will ask you, I think I put 3 different questions on midterm 2 about state the defining equation for this, that, or the other, or state the equation that is only always true inside blank. You have to be able to distinguish between universal truths that are always applicable and equations that are true in some contexts versus the other. It's not just me being picky, this, if you understand context, if you can pick up on when what applies and when what doesn't apply, you're more likely to get everything righter. But I do want you to pay attention to this. And I'll give you additional practice in this in a smidge. Okay, so Google question A, show me what you think. How do I change the capacitance of a capacitor? What affects the capacitance of a capacitor? In particular, how do I double the capacitance of a given capacitor? And if you think that the only answer is have the voltage applied, just say 1. If you think that have the voltage applied and double the plate area, I would say 1, 3 or whatever. I don't know. I have a capacitor. I want to double its capacitance. What can I do? Let me go back for a second. If I double the voltage across a resistor, how does its resistance change? If I double the voltage across a resistor, how does its resistance change? What did you learn last year, last module? It doesn't. The electricity applied to a resistor doesn't control the resistance of the resistor. What I was just going on about. The resistance of a resistor is controlled by the material, size, and shape of the resistor. So you should consider with capacitance, what controls the capacitance of a capacitor? Let's see, I want to write this in this way. Okay, what is always a true statement? Capacitance is equal to charge per volt. But how do I get a given capacitor? How do I get a given capacitance? I get a given capacitor to have a given capacitance by its size and shape and materials, but we're not talking about dielectrics in this class. MCAT students, you'll learn about another factor, a third factor in there, which is called dielectric. Ask me in the MCAT study sessions if you wish to know more. So if I want to get a given capacitor to have a given capacitance, I control the capacitance of the capacitor not by the electricity on it, applied to it, but by the size and shape of the capacitor, its area, its plate separation. The correct answer here is 3 and 4. 3 and 4 only. If I half the amount of voltage on a resistor, I will half the current through it, not the resistance of it, right? If I have the charge on the capacitor, I won't have the capacitance. What will happen is the voltage will decrease. The voltage will go down. Think about capacitance like the size of an air tank. The more you pump up an air tank, scuba diver air tank, right? The more air you put into the air tank, the higher the pressure goes. Pressure is voltage, amount of air is charge, right? PV equals nRT says pressure goes up the more N you have, right? Everyone's learned that? Okay, the volume of the tank is the capacitance, if you will. It is the ratio of how much material you can get in the tank. I'm ignoring temperature. How much material you can get in the tank to how much pressure is developed across the tank. If I've got a big honkin' storage tank versus if I'm trying to pack into a little emergency thing, it's a lot easier to pressurize the big storage tank. So let me ask you this. If I've got an air pump and a storage tank, and I double the pressure inside, does that make the tank bigger? No. If I double the pressure inside, I'll double the amount of air inside. I don't double the amount of the volume without it changing the device. So here, if I have the voltage applied or double the charge applied, that will change the charge, that will change the voltage. That doesn't control the capacitance. This is what controls the capacitance, the size and shape. Please, Selena. Mm-hmm. That's true. C does equal Q over V. That's a true statement. But just because you've got an equation, when you have an equation with three variables, oh, we talked about this last week too. If you have an equation with three variables, you don't know just by looking at the equation if this controls this, or this controls this, or this controls this. You have to know something about the meaning of these. Meditate upon this, my grasshoppers. Your weekly earnings equals your hours times your pay rate, right? Right? If you take your take-home pay and divide that by the hours worked, that's equal to your earnings. If you double the number of hours worked, does that double your salary? If you work for twice as long, does that double your pay rate? Sorry, your pay rate, not your salary. If you have the number of hours that you work, you get paid less. It's not that your wages go up or down, right? So you have to think about what controls what. Your pay rate, capacitance in this example, how many dollars per hour you make, that's a function of how much our capitalist overlords like you, or your qualifications, I don't know. How many dollars per hour you make is not controlled by the time that you work and your total wages, your total earnings for the week. You could use the idea, divide the amount you earn by your hours worked and get your pay rate. That's always a true statement, right? Assuming you're hourly. But just because this is always a true statement doesn't mean that changing your pay rate, that changing your hours worked controls the dollars per hour that you make. Go back to, I've got an equation that has three variables in it, and ask yourself, go get away from that and ask yourself, what controls what? What is the nature of this object, that object, or the other object? Follow-up question. Suppose I can change the size and shape of the capacitor and also attach it to a circuit or detach it to a circuit. If I have a capacitor attached to a battery and I double the plate separation, what would happen? If I double the plate separation, if I increase the plate separation on the capacitor that is hooked up to a battery, what would change and what would be held constant? Google form, answer me this. What variables would change? Let's say Google form B. I doubled the plate separation of a capacitor attached to a battery. What is held constant is B. What changes is C. Just list the variable names. C, A, Q, V, what? Let me write this down. A capacitor is hooked up to a battery. D doubles. I pull the plates further apart of a variable capacitor. Google question B. What did I ask first? What remains the same? Is that what I said when I first stated it? List the variables that remain constant. Google Form C, what changes? Just list the variable. Of these variables, capacitance, charge, voltage, area, distance between the plates, what controls what? I'm hooked up to a battery. I change the plate separation. What is changeable? What is fixed? Okay, so let's reason about this. If I change the physical dimensions of the capacitor, the capacitance has to change. That's what makes a capacitor's capacitance capacitate, have a given value. So one thing that changes is the capacitance of the capacitor. I mean, I'm assuming the area doesn't change. If I also change the area, if I halve the plate area and halve the distance between them, then I could keep the capacitance the same. But I didn't say anything about that. So if there's no reason to believe that you're changing the capacitor in two ways, you can also say that the area will remain constant. Really, I should have reasoned about this one first. If this changes and this stays the same, then this can change. All right, if capacitance changes, I am changing the left side of an equation. Does Q change? Does V change? Do they both change? Well, you have to reason about more than one component. What did I say? A capacitor is attached to a battery. And what do you know? What have we learned about batteries? What do they do? They hold constant voltage. If the battery keeps the voltage constant, then what must be changing in response to changing capacitance? The charge on the capacitor must shift. If I pull the plates further apart, there's less capacitance to be held. Some of the charge will flow backwards onto the battery. The battery is trying to keep a constant voltage. It doesn't need to push. It can't push as much charge when there's less capacitance. Question me. We did this last week. Do you remember? And do you remember the why? Do we move on or do you have questions? I love questions. Okay. I will remind you, by the way, I will remind you that the kinetic energy formula is 1/2 mass velocity squared, and that the total amount of energy of the electron is not going to change. Energy in this case is going to go from kinetic form to potential form. You must, in order to solve this problem, you must write an equation. Notice I am not asking for you to plug in numbers. I am asking for you to write an equation which relates energy to stuff and write an equation which relates energy to stuff and solve for V initial. If I remember correctly, last year students had an enormous amount of difficulty with this problem. I'm going to give you 2 minutes to get this started, and then I'm going to give a hint. Ooh, no, you don't like this at all. Who's totally, as my 2-year-old would say, guck? Means stuck. No? Making progress? You're guck? You're guck? Here's how to start. Start by writing down the initial total energy. Start by writing down the final total energy. What form or forms of energy do we start with? What form or forms of energy do we end with? Write that as an equation. I have written my first part down. I think that the electron starts with some motion because I'm told that it has an initial velocity, initial speed. I think that I'm told that it ends with a final speed. I'm sorry, I'm given a final speed. I'm asked for the initial speed. Hint, it's got motion in both initial and final. Okay, so what other form or forms of energy are present? Well, I think there's electrical energy present. And then I challenge you to tell me, what is the equation for electrical energy? What is the always true equation for the electrical energy? I've got a given charge. I've got a given voltage. It's the relationship between these things and energy. You must be able to define voltage and energy in this relationship. Please, somebody tell me what voltage and energy, how voltage and energy are related. Free response. This is not looking good, y'all. I really hope you're shy. Google question D. What is the defining equation for voltage that is always true, not just in a particular component? Google question D. What is always true about voltage? What is true about voltage? Voltage. Okay, so here we go. Voltage is defined as potential energy per test charge. That is to say, voltage is defined as energy divided by charge. I can solve this equation, U divided by Q equals V, for potential energy, and I get U equals Q times V. If this is fuzzy, then you be trying to learn a foreign language class without memorizing any vocab. This class gets a lot easier when you know your foundations. No, not just have on your equation sheet. This is something that you should memorize. Potential energy equals charge times voltage. Okay, so if I have this equation, please note that this V is voltage and these V's are velocity. I usually make velocity V's lowercase v, voltage V capital V. If I have this equation, can I say that initial equals final and solve for initial? Ready, set, go. This is Google question E. Can you set these equal and solve for V initial? Solve for VI. Yes is not what I'm looking for. Solve it, solve it. Practice your algebra skills. Hmm. I will remind you that what you do to one side, you must do to the entire other side of the equation. You must do the same thing to both sides of an equation. Okay, let's do algebra. What do I want alone? V initial. Now there's stuff attached to it. There's a half m, there's a plus qv. What order do I do things? Do I get rid of multiplications or do I get rid of additions first in algebra? Here's how to figure out which. Order of operations sucks. PEMDAS sucks. Go backwards. If you were evaluating this, first I would square, then I would multiply, then I would add, right? Order of operations, first I would square v, then I would multiply by m and times a half, then I would add plus qv. When you're algebraing, you do that backwards. First, I'm going to remove the added quantity. How do I get rid of q times v? It is added on, so what do I do to both sides? I subtract off. Second step, if I were evaluating, I would square first, then I would multiply by half m. If I'm algebraing to get v initial, I would multiply by 2 over. If I want to get rid of the multiplier before I get rid of the square. You undo order of operations. So how do I get rid of half m? I think multiply by 2 over m. If I multiply the left side by 2 over m, I get v initial squared equals v final squared minus qv, right? But half of you did. That's not correct. If I multiply both sides by m over 2, I need to multiply each term. Sorry, 2 over m. I need to multiply each term by 2 over m. If you have two things added together and then you multiply, you can't just multiply on one term. You have to multiply all the terms. Yeah, you see it? 2 times 3 plus 4 is not 2 times 3. 2 times 3 plus 4 is 2 times 3 plus 2 times 4. And you can't ignore one of the terms. You multiply both of these by 2 over m. Okay, and the final step. How do I undo a square? With a square root. Now, when I square root a sum, can I break that apart into 2 square roots? No. Square root of a sum is not the same thing as the sum of the square roots. My final answer is root v final squared minus 2qv over m. There's more than one way to write this, by the way. If you're given capacitance and electric field, you can reshuffle these terms in a couple of different ways. I think this is the straightest forward way. Great. Now let's plug in numbers and see if you can get answers. Please take a note, by the way. What's a pico again? Pico is 10 to the negative 12. What's a kilo? 10 to the 3, 1,000. Yeah. Okay, let's see just how much a vacuum tube circuit capacitor can accelerate. Oh, I need to give you constants, don't I? Um, and charge of an electron. 1.6, 10 to the negative 19. And this is F, by the way. Let me see what you get. Correct answers. I love correct answers. The person who asked, "How am I supposed to type it in?" Yeah, that's reasonable. Any sane way of what you said is perfectly fine. If you're missing, okay, it's fine. Please note that charge of the electron is negative. The electron is attracted, should be darn speeding up. The initials should be slower than the final. And I'm asking for the initial, and it is attracted to the positive plate. Your initial had better darn well be smaller than your final. Now I'm the one not thinking clearly. The initial needs to be slower than the final. The charge on an electron is negative. That's true. But let's see, what sign does it make sense to have here? Should I be less than subtracting off a positive number, or should it be greater than subtracting off a negative number? The direction that the electron goes, it is gaining energy. So if I'm looking for the initial, I need to be subtracting off a positive amount of energy. It doesn't actually make sense to use the negative sign here. If I'm starting with my initial energy as QV, that's an initial positive amount of energy that I lose going to the plate that it's attracted to. So it does not actually, I gave a misleading hint. We should not use a negative number there. If I subtract off a negative, I will speed up. So plug in the magnitude of the charge here if you want to predict a slower initial speed than final. Apologize for the misleading hint. More people got this than the algebra part. Okay. Let me... Question. I pulled out a 10 to the 14. Root 10 to the 14 on each term pulls out as a 10 to the 7. You're talking about going from here to here? If final velocity is squared? Yes. Yes, because the square root does not just kill one of the terms. If I have, look, example, square root of 9 minus 25 minus 9. Is the square root of 25 minus 9 the same thing as 5 minus 3? Let's test. What's 25 minus 9? 16. What's the square root of 16? 4 is not equal to 5 minus 3. So you can't take the square root of the individual terms in here. You wouldn't take the square root of 5 squared. You have to leave it as 25 minus 9, or v final squared minus 2qv over m. That's part of PEMDAS, by the way. Wait, that's not a true statement. No, that's simply rules of exponents. It's not PEMDAS. Other questions before we move on? Okay, this is leading to something muy importante. I want you to think about this because this goes back to the essence of capacitor energy, of energy and voltage and capacitance. If I have a charge in a capacitor, a single charge in a single applied voltage, I multiplied charge times voltage to get energy. Energy is charge times voltage. Yes, if I've got a charge feeling some external voltage. There's also charge on the plates of a capacitor. A capacitor has a charge, a capacitor has voltage. If I multiply the charge of the capacitor by the voltage of the capacitor, I will get the wrong answer for calculating energy of a capacitor. If I ask you about a charge inside a capacitor flowing around, QV makes sense to use. Because this charge, this individual little charge, a single electron floating around in between the plates of the capacitor, this single electron is not what is responsible for making the capacitor have that V. The Q here and the V here are independent. But if I've got a capacitor charged up by its own Q, you have to use, briefly, here's the punchline of the story I'm about to tell, you have to use half QV to find the total energy of the capacitor. Okay, here's why. And if you think through this, this actually should make some kind of sense. Why does a capacitor have energy at all? Well, let me ask you, why does an air tank have pressure in it at all? Because the air is compressed. It doesn't want to be packed in right next to each other. The electrons on the negative plate and the positive charge on the positive plate of a capacitor doesn't want to be stuck near other negatives, doesn't want to be stuck near other positives. So as a capacitor is charged, as I apply a battery and build up the charge on a capacitor, I am storing energy in it. Each little bit of charge that goes in, every little single electron that flows in, feels a different amount of voltage on the capacitor. The very first electron feels no voltage, right? Because there's no charge built up on the plates of the capacitor, no charge, no voltage on the capacitor. So the first charge that flows into the capacitor does not feel any voltage. The middle charge, the halfway up charge on the capacitor, when I look at the electron that flows on halfway through charging the capacitor, that guy feels half of the final voltage, right? The last charge to fill up on the plates, the very final amount, is feeling the fully pressurized capacitor's capacitance. If I just look at the total charge times the total voltage, the total charge times the total voltage, I'll get a misleading impression of the energy stored. I have to look at the voltage generated by the test charge as it accumulates. The first bit of charge that goes on feels nothing. The last bit of charge feels everything. Every bit of charge that flows on feels the voltage due to the pre-existing charges, and then that bit of charge increases the voltage for the next charge. It is harder and harder to pump the capacitor up. The more voltage is on it, the more charge that's on it, the harder it is to push additional charges. So, if I just multiply total times total, I will not get the actual charge energy stored in the capacitor. Again, I want you to think through the nature of charging the capacitor. The very first electron, the very first positive charge to flow onto the respective plates of the capacitor, if there's no charge already on there, it doesn't cost any energy to go there. QV tells the amount of energy it takes that one little Q to suffer that one little amount of V. And if V starts at 0, Q times V is 0. As the capacitor gets more and more charge, its voltage goes up. As its voltage goes up, it is harder and harder to push additional charge on. The final charge, the last charge that deposits, feels all of the final voltage. Do you remember, once upon a time, I had the equation not just distance equals final velocity times time, but average velocity times time. Do you remember that from last semester? Average velocity times time? If I start at 60 miles an hour and I end at 60 miles an hour and I drive for 2 hours, I'll go 120 miles. If I start at 0 miles per hour and accelerate to 60 miles an hour over the course of 2 hours, whew, my car sucks, then it would go a lot less distance because I'm not always going at the final speed, right? Same thing here. If I look at the average charge or the average voltage times the total charge, I get a factor of 1/2. If I were starting from halfway charge, this would actually be the average voltage times the total charge, but I'm always going to talk about the capacitor from as relative to uncharged. We're never going to use the average voltage times the charge, or rather this is the average voltage, but I'm always going to use initial voltage as 0 in this equation. See where that comes from? This is actually average times total, just like with 1/2 final velocity times time tells you how you speed up from rest. So the energy stored in a capacitor because of the charge on the plates of a capacitor is 1/2 times the charge of the capacitor times the voltage of the capacitor. Why do I use a capital Q here? To remind myself that this is the charge that is the cause of this voltage. It is also the charge that is feeling this voltage. In a way, it's both capital and lowercase, both source and test charge at once. Do not mistake these equations for each other. If I've got a free charge floating around, feeling some voltage difference from here to there, QV. If I've got a capacitor with some charge on it, half QV. Context? Makey sensey? I ask you then, Google questions G and H. Tell me, can you plug in? I'm going to give you total charge times total voltage. And I'm going to give you that charge equals capacitance times voltage. I'm going to ask you to rewrite this without Q. And Google question H, can you algebraically rearrange without V? Potential energy in the capacitor equals blah. Potential energy in the capacitor equals blah. Sometimes one of these forms will be more useful, sometimes the other. I want you to plug in and solve for u. Plug in and solve for u. I mean, it's already solved for you. Plug in and simplify. Plug in and simplify. And solve for u. Okay, so I use the principle of algebra, which is to say, if I know what a letter is equal to, I can write that letter instead of, I can write the expression instead of that letter. If I want to eliminate q, I'm going to write this equation again, except instead of q, I'm going to write what q is equal to. Oh, v times v, that's a little ugly. I choose to write this in the advanced notation v squared. Likewise, if I want to get rid of the v, I can take this equation, solve for v. V is q divided by c, and plug in. For God's sake. Now, I don't like 1/2 times q over c, so I'm going to rewrite that as q squared over 2c. Please note that the c is downstairs, not q squared over 2 times c, q squared over 2c. Sometimes you will be given capacitance and voltage. Which formula would you use? The one with capacitance and voltage in it. Other times you'd be given charge and capacitance. Which formula would you use? Well, look at what you've got and plug in. If you forget these equations, you can always do a two-step. You can find an expression using Q equals CV. You'll have an unknown left, and plug that unknown in for the other expression. You could solve in two steps instead of solve in a single step. But Merry Christmas, this is, I think, half the homework, is these two, what we've just done. Okay, before we do our final example, what the hell, let's do one final example. Here, find the energy in joules of a 100 microfarad capacitor with 12 volts across it. Think about what you're given and what you need. This is Google question I. Let's see where you're going. So let's see where you are. What's a micro? -6. Micro millionth. All right. Vast majority have got it. I get 7.2 millijoules, or 7.2 times 10 to the minus 3 joules. Watch your order of operations. There are a couple of people who are not following the rules. PEMDAS people. PEMDAS. But I want you to take, let's see, it is 12. Take 1 minute, turn to each other, or go over your notes and look at what have we just done? What does it mean? What is the context? And then ask me a question. And then we'll get out of here. Oh, this room feels so eepy. I'm eepy too. Okay, ask me a question. Got 2 minutes left. Selena. Mm-hmm. 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 Algebraic theory range. Good. Other question. Okay. Someone asked in the Google form for the formula we developed here, when would you use plus and when would you use minus? Well, I should have made a deal about this before. Hell, I fell into the trap myself for a moment. Think about, does it make sense for the charge to be speeding up or slowing down? I had an electron attracted to the positive plate of a capacitor. It's speeding up, that's attracted. The velocity must increase. The earlier velocity, the initial velocity, must be less than the final velocity. So I think it makes sense to subtract off that part of the energy. Subtract off the positive number here. I'm not going to plug in negative q. Subtracting a negative would increase the initial velocity. That would be slowing down. That's not impossible. If you forced an electron to go from the plus plate to the minus plate, then that would be the initial velocity. The initial velocity would be faster. But as I was encouraging you to do once upon a time last week, is to think about, well, what does it make sense to have? Is this helping, hindering, going up, going down? The more you think about that, the more likely you are to catch mistakes in the first place. Last chance for a last question? Nothing else seen on the Google forum? Okay, we're out of here. I will see you on Wednesday. And then I won't see you because break.